Okay. So we had that theorem that said the three angles of a triangle at 180. We were going to call it the triangle angle sum theorem. That is going to lead us to some other facts today, and they're easy conclusions to get to, but we're going to obviously use those over and over again throughout the year so we can talk about them. But before we get into this stuff, I want to make sure that we all understand kind of what mathematics is about, because I think a lot of us are made, and I've got a document to let you read to kind of restate this maybe next week at some point. But I think a lot of people think mathematics is all about calculation. It's all about adding numbers, subtracting numbers, multiplying, dividing, that kind of stuff. Okay? Where if you think about it, and I think maybe we've talked about this in this class a little bit. If I think about adding, you all know how to add. You start doing that in like the third grade, second grade, whatever. Okay? But adding is a more efficient way of counting, isn't it? If I had 5 people in this classroom and let's say 12 people in Mr. Malk's classroom, and I didn't know how to add, to see how many I have, I would come in here and count 1, 2, 3, 4, 5, and I'd go over to his room and start at 6, 7, 8, 9, 10, all the way through, right? Does that make sense? If I know how to add 5 and 12, that gets me that sum of 17 much quicker than counting, correct? Okay. So then we get to multiplication. And multiplication, if you think about multiplication, that is just repetitive addition. 2 plus 2 plus 2 plus 2 plus 2. So adding those together makes more sense to call that 2 times 5, right? And I get 10. Okay. So my hope is that we realize then that adding is just a more efficient way of counting. Multiplication then is a more efficient way of adding. Therefore, multiplication must be a more efficient way of counting. Does that make sense? Okay. And then we get to subtraction. Subtraction says we're going to remove things, right? So it's kind of like counting backwards. Okay. And then we get to division. And let's talk about division real quick. If I ask you that, what's the answer to that? 3. But it's really telling me how many times you can subtract 4 from 12. How many times you can subtract 4 from 12. Okay? So division is just repetitive subtraction. Would you agree with that? How many times I can subtract 4 from 12? Okay, do you guys remember in Algebra 1 what they defined subtraction as? What did they say subtraction was? Adding the opposite, right? Okay. Subtraction, by definition, is adding the opposite. That means, by definition, subtraction is addition. Okay. So if we think about all the things that we just said, division is subtraction, but subtraction was addition. Multiplication was repetitive addition. Isn't all 4 operations just addition? Which addition, we said, was like a more efficient way of counting, right? So our operations that we have are just designed to allow us to do things more efficiently, okay? When we write all these theorems, okay, and today we're going to see some other types of statements called corollaries. When we come up with those facts, it allows us, so mathematics is about trying to create relationships that allow us to circumvent, to go around, to eliminate the amount of calculations that we have to do to get a true answer, okay? And geometry is maybe the first time that you're starting to see that, starting to realize that I'm not being a calculator anymore, okay? I would think you would agree that a lot of the things that we've done so far this year has removed the idea of being a calculator, right? Removed the idea of arithmetic, okay? And we're more now interested in relationships that allow us to kind of bypass that stuff, okay? So we're going to talk a lot about the facts of triangles that allow us to bypass really the triangle angle sum theorem and using that in its entirety, okay? If we get ourselves in that mind frame, I think this class makes a whole lot more sense, okay? A triangle is a figure formed by 3 segments joining 3 non-collinear points, Okay. Key word here is that the 3 points have to be non-collinear. If I were to take this point, and that point, and I were to connect them, I don't get a triangle, correct? A triangle has to be a polygon. You guys know what a polygon is? If I take, just kind of give you some polygons here real quick, and we'll just use our most simplistic version, and most, I don't want to say simplistic, but real nice version of particular polygons. So let's say we go from 3 to 50 increments of 1. All right, so here I've got a polygon. Okay, that's a polygon. That's a polygon. That's a polygon. These are all polygons. Does that make sense? Okay. Now those are a special category of polygons. Those are called regular polygons. Okay. So you got your stop sign there, right? Okay. Octagon. But this is also, let's see here. That is also a polygon. Okay. It's just not a convenient polygon. It's called an irregular polygon. I don't know how many sides are there, but you can count them and if you say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think there's 10 sides there, maybe 11 sides. If it's 10, it's a it's a decagon. If it's 11, it's a neagon. But it's a polygon. What is the difference between that shape and maybe, let's say, that shape? Because that shape that I just made is not a polygon. What's unique about that shape that I just made? It has a part of a circle, isn't it? Do you agree with that? There's a curve there, right? Okay. Polygons can't have curves. They have to be comprised or composed of strictly segments. Okay. So our triangle is the first one of those that can be made. It's the smallest type of polygon we can ever create. Okay, and what is nice about a triangle is that, let's go back to this picture here. If I were to maybe do something like that. Okay, I take that octagon and I just broke it up into a bunch of triangles, right? So if I can understand something about a triangle, I can understand something about that octagon. Okay, if I look at even at this one, now this is just one way of breaking this up into triangles. But every shape there now that comprises that thing is a triangle, right? Does that make sense? So our triangles are building blocks of all other two-dimensional shapes, and eventually our three-dimensional shapes. Okay? So that's why we're going to investigate triangles a lot. You're going to think that that's all we talk about is triangles, and that's really what we are going to do for about the next probably 15, 16, 17 weeks. Talk strictly about triangles. Because when we learn so much about those, it should be a very easy discussion then to talk about those other figures. Okay? In regards to doing that, we need to be able to discuss and categorize and describe certain types of triangles. And we can do that based off of their number of sides that are equal or congruent and by the number or some characteristics of their angles. Okay? Now, some of this, so these are basically going to be adjectives for triangles. Okay, they're going to be ways that we describe a triangle, right? You can kind of take one statement out of like scalene, isosceles, or equilateral, and maybe pair it up with one of those acute, obtuse, right, or so forth. Okay, so we're going to talk about that as we move through. But so these are not strictly say I cannot just have only a scalene triangle and it not be classified as acute. I can have acute scalene triangles. Okay, so scalene refers to the number of sides that are congruent, and scalene means no sides congruent. Hopefully that's a fact that maybe you've heard before, or a word you've heard before. Okay? Isosceles, this is where maybe in other courses you were led astray. Isosceles, a lot of times you would say it was two sides are congruent. The correct way of talking about isosceles is that it's at least two sides congruent. So if all three sides are congruent, it's still isosceles. Does that make sense? Okay. However, if it's three sides, okay, we can better describe it and classify all three sides congruent. We call that equilateral. Okay. So here's the idea. I'm going to ask you a question. Is an equilateral triangle isosceles? So an equilateral triangle has three sides that are congruent, right? Does that meet the definition, or does it exceed the definition of isosceles? If you have three sides congruent, is that at least two? So it meets the definition or exceeds the definition of isosceles. So every equilateral triangle is isosceles. But if I ask you, is every isosceles triangle equilateral, that'd be no. And the idea here is if I ask you close your eyes and I put a triangle in front of you and I told you it's isosceles, you can't tell me whether it's equilateral or not. But if I told you that the triangle in front of you was equilateral, you can 100% definitively tell me it's isosceles. You can tell me it has two sides congruent. Okay? So that's how we're going to talk about them in regards to the number of sides that are congruent. Okay? The next category is based off of relationships with their angles. Okay? If we have an acute triangle, all three angles are going to be acute angles. So all three angles will be less than 90 degrees. Okay? Now, you can have an acute triangle that is also scalene. That is possible. Acute that is also scalene. You can also have an obtuse triangle that is scalene. Okay? You can have a right triangle that is scalene. Okay? Does that kind of make sense? So we can take these adjectives and kind of group them together. Okay? You can have an acute triangle that is isosceles. You can have an obtuse triangle that is isosceles. You can have a right triangle that is isosceles. And all equiangular triangles are isosceles. And we'll talk about that here in a little bit. So you can take those angle classifications and pair them with the side classifications as necessary. Obtuse means you have one obtuse angle. Okay? Why can't I not have two obtuse angles in a triangle?
That adds more, like it adds up to 180, like more.
Okay, so good. So if I have two obtuse angles, so obtuse means bigger than 90, right? So if I say that like 90.01, that's an obtuse angle. If I had two of those in a triangle, that'd be 180.02. And that violates the triangle angle sum theorem. And we've talked about how one rule cannot violate another. One relationship cannot violate another. Okay? So the same reason exists for a right triangle. I can never have two right angles because then I don't have room. I get exactly 180 with two right angles. So I wouldn't have any degrees left over for the third one. Okay? Equiangular means all the angles are congruent. Okay? So here's my question. If all angles are congruent, you should be able to maybe classify that a little better or give me a fact about it a little bit better. If I say all angles are congruent, what is the measure of each angle? 60. Okay? So each angle in an equiangular triangle is 60 degrees. Okay, 180 divided by 3. Basically, you're finding the average then. I'm going to take 180 divided by 3. Okay? That last phrase there, I think that it's probably better to write this way. A triangle is equiangular. And then right there, write the phrase, if and only if. Okay? If you want to use IFF, remember that was the abbreviation for if and only if. A triangle is equiangular if and only if it is equilateral. That means if I tell you you have an equiangular triangle, you can automatically tell me, well, it's also equilateral. And if I read it backwards, it says, if it's equilateral, you automatically can tell me it's equiangular. Okay? Equiangular, they're all 60 degrees. So if I tell you you have an equilateral triangle, even though I've given you all the information about the sides, it's equilateral. Lateral means sides, right? If I tell you that, you can actually tell me stuff about the angles. You can tell me you know the angles all have to be 60 degrees. That's a unique fact about that type of polygon. So if I tell you, close your eyes, and I'll put an equilateral triangle in front of you. Let's do it this way. Close your eyes and put an equiangular triangle in front of you. Is it isosceles? If it's equiangular, is it isosceles? Yes, it is, because if it's equiangular, you know it's equilateral. If it's equilateral, you have 3 congruent sides. If you have 3 congruent sides, that exceeds the definition of isosceles, so it must be isosceles as well. And we can classify it that way. And now the reason we want to talk about that is later on in Chapter 4, we're going to have rules, facts, theorems, postulates, that kind of stuff, for isosceles triangles. Well, then those rules are going to play over into being able to be used inside equilateral triangles too, because equilateral triangles are isosceles. Okay, so it's important to be able to know kind of that distinction between these things. Okay, the next thing we want to talk about. Now you don't need to write this theorem down because we've already written it before, but I want to talk about something that's called a corollary. Okay. A corollary is kind of like a little brother to a theorem. Okay, it's not as important as a theorem. It is a true fact, but it's not as difficult to prove as theorems are. Okay, and they usually are like 1 or 2 steps to prove, and the proof comes directly from the theorem. So they're actually pretty easy. They're like I said, like a little brother to the theorems. So I want to describe these, talk about these, and then we'll kind of, as we go through each one, kind of draw maybe a little bit of a picture for them or an explanation for them. But the first one says, if 2 angles of one triangle are congruent to 2 angles of another triangle, then the third angles are congruent. Okay? Our textbook calls this a corollary. Some textbooks call that a theorem. But the reason our textbook calls it a corollary is this idea here. If I've got triangle A, B, C, and I've got triangle A prime, B prime, C prime. Somebody give me a number. 15? Okay, so let's say A is 15 degrees. So what's A prime? If these 2 things are congruent. 15 degrees. Give me another number. 4? So let's say angle B is 4 degrees. So B prime is also 4 degrees. Would you guys agree that that meets the idea if 2 angles of one triangle, so 2 angles of the top triangle, are congruent to 2 angles of another triangle, 2 angles of the bottom? How many degrees have you chewed up top for those 2 angles? 19 degrees, right? How many have you chewed up for the bottom? 19 degrees, right? Now, both those figures are triangles, so both those figures should have a total of 180, right? Well, how do I find angle C then? I take 180 and do what with it? Subtract 19, right? Well, do you do the same thing to find C prime? Take 180 minus 19? So the idea is that this theorem, or sorry, this corollary comes directly from the fact that both those triangles have 180 degrees in them. Okay? So in that case, both those angles would be 161. Okay, so like I said, sometimes they call it the third angles theorem. In other textbooks, ours calls it a corollary and does not give a name to it. We will talk about that again in the next couple of sections. I'll actually write it out again for you because we use it so much in this course. Okay. Each angle of an equiangular triangle has measures of 60 degrees. Okay, I kind of already talked about that, but this is that idea. If I have a triangle and I have 3 angles in it, would you guys argue, let's say I've got this triangle, that's 1, that's 2, and that's 3. And I tell you that it's equiangular. Wouldn't you be able to say that measure of angle 1 then is the same as measure of angle 2, which is the same as measure of angle 3? Does that make sense? So does that mean then everywhere that I see 2, I can replace it with 1 because that's what it's equal to? And everywhere I see 3, I can also replace it with 1 because we have this rule that says they're equal? So if I do that, don't I get measure of angle 1 plus the measure of angle 1 plus the measure of angle 1 equals 180? Does that make sense? How many measure of angle 1s do you have there? 3 measure of angle 1s equals 180. So what's measure of angle 1 equal? 60. But measure of angle 1 right here said was the same as 2, which was the same as 3. So aren't they all 60? Okay. We didn't use really any other geometric property other than the fact of knowing that there was 180 degrees in that first triangle. So that's why it's a corollary. We can easily prove that using only that geometric fact. Okay. The second to last bullet there says in a triangle there can be at most one right angle or one obtuse angle. Kind of already talked about that. And that is so that we don't violate the 180 degree total. And the last one says the acute angles of a right triangle are complementary. What's complementary mean? Two angles that up to 90, right? So if I know that I've got a right triangle, here's my right triangle. How many degrees is that right angle right there? 90, right? Okay. So if I've got measure of angle 1, call that 1, call that 2, plus the measure of angle 2, plus, now this angle here we know to be 90, right? All three of those are going to add to 180, right? Well, then measure of angle 1 plus measure of angle 2, a little bit of subtraction there is going to give me 90 there. And that says we have two angles that add to 90. So two angles that add to 90, by definition, are said to be complementary, right? Okay. So a lot of people, when I give you maybe a question like this, I ask you, solve for x. I say, like, that's 2x. And I say, that's 3x. A lot of people are going to go, oh, 2x plus 3x plus 90 equals 180. And by our triangle angle sum theorem, they are absolutely correct, right? But if I want to be a little bit more efficient, and this is the idea of mathematics, and then these rules that we're coming up with, I should know that that's a right angle. So these are the two acute angles of a right triangle. They are complementary. And that bypasses the algebraic step of having to move that 90 over. And that's the purpose of our theorems. Now you might say, well, okay, I learned that theorem and I consume that amount of space in my mind so that I can save subtracting 90 from both sides of an equation. That maybe seems like a little bit overkill. Eventually, though, you're going to find out how useful that type of thing is. Okay? Especially the harder these expressions get, and that's the idea. Okay? That's the whole concept of mathematics. It's trying to circumvent, simplify, make calculations a little bit easier. Okay? All right, so we got one more theorem here I want to talk about. But before we get there, we need to talk about some vocabulary. Okay? Whenever we take a triangle, okay, you have three sides of your triangle. Three sides of your triangle. You are able to extend any one of those sides. So what we've got here is we've taken from that point, we create that segment right there. But every segment of a triangle is a part of a larger line, right? Does that make sense? Or part of maybe a larger ray. So what we do is we trace that segment out, but then if we keep passing through that point, that vertex of our triangle, we get that description, that picture, we create an angle on the outside of our triangle. Would you guys agree with that? Would you agree that this here is an angle? Okay? Now, because it's on the outside of our triangle, we call it an exterior angle. Okay? So that's a vocabulary word, exterior angle. The angle created when we extend one side of a triangle. So if I went and extended this side. Okay, now you want to keep it straight, so extended that side. That would be an exterior angle. If I extended the bottom side, that would be an exterior angle. Does that make sense, everybody? Now you can go in the opposite direction as well. So you can go there. So this would be an exterior angle. That would be an exterior angle. And I come over here, that would be an exterior angle. If I put them both exterior angles that exist at each vertex, what do you notice about that angle there compared to that angle there? They're the same. They're vertical, right? Okay. But generally speaking, we only look at one exterior angle per vertex. Okay, so just looking at that one, that's an exterior angle. So then, if I've got angle 1, 2, and 3, those are angles that are on the inside of my triangle, right? So collectively, those are called interior angles, because they're on the inside. Okay. Now, angles 2 and 3 have a special adjective to them. Okay, call them remote interior angles. What's the word remote mean? Or where do you see or encounter the word remote in your everyday life? Controls, right? Okay. So I got a remote control back here for my projector. Okay. My mouse is kind of like a remote control for my computer. But if I'm sitting on my TV, or sorry, I'm not sitting on my TV, sitting on my couch at home watching TV, if I sit on my TV, my wife would probably divorce me. So sitting on my couch watching TV, I want to use my remote control to control the TV, right? Why is it called remote? What does that mean? Or if I'm on a remote island, what does that mean? By myself, okay, by myself, if I'm watching TV at home, I usually am by myself, but if I'm by myself, I'm far, on a remote island, I'm far away, right? Does that make sense? Okay. If I'm using my remote on my TV, the idea is so that I'm far or further away from my TV. I'm not, if I had to go up and change the TV on the actual TV, or change the channel on the TV, that'd be a pain in the butt, right? So the remote is to allow me to do that from far away. Okay? So whenever you see the word remote, it means far away. Would you agree that your angles 2 and 3 are the ones that are far away from that exterior angle? They're, by definition, they're essentially in a triangle, they are the non-adjacent angles to the exterior angle. So 1 would be adjacent to the exterior. 2 and 3 then by default are the ones that are far away. They're the remote ones. Okay. Now the reason we want to talk about that is if I look at that picture right there, give me some facts that you know about the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3. What would you tell me about those? Okay, that's a 180, right? That's a triangle angle sum theorem. Okay? What would you tell me about the measure of angle 1 plus the measure of angle 4? They have to 180. Why? They're supplementary, but why do you know they're supplementary? They make that line, right? So they're a linear pair. Okay? What do you know about that 180 and that 180? They're equal. So doesn't that mean that thing there and that thing there are equal? So let's do that. Let's put those equal to one another. So let's go measure of angle 1 plus measure of angle 2 plus measure of angle 3 equals the measure of angle 1 plus the measure of angle 4, right? What's on both sides there? Angle 1. Does that amount cancel each other out? So you're left with the measure of angle 2 plus the measure of angle 3 equals the measure of angle 4. What kind of angle is angle 4 itself? It's an exterior angle, right? What are 2 and 3? Based off of 4, their remote interior, right? Okay? So 2 and 3, so the sum, what we're saying here is the sum of the remote interior angles is exactly the same as the exterior angle. So I'll let you write that theorem down. The measure of an exterior angle is equal to the sum of its 2 remote interior angles. Okay? And what we need to understand, though, is that the remote interior angles are going to change based on which exterior angle we're looking at. Okay? So for this picture, 2 and 3 are the remote interior angles because I'm looking at angle 1. Okay? If I were to redraw and maybe do it this way, and that, so assuming that those 2 triangles are kind of the same triangle, just looking at a different exterior angle, now you can see 2 and 3 are kind of positioned in a different position, right? Okay, in different spots. So remote interior angles are predicated, or they're determined based off what exterior angle you're looking at. Okay, and then once you find the exterior angle you want to deal with, then that's going to define what your remote interiors are. But measure of angle 1, the exterior angle is the same as the sum of the 2 remote interior. That's a common question on the end of course exam, okay, to understand that relationship. So, kind of do some examples here. I'll give you a minute to maybe draw that picture. All right, so this type of question, you cannot tell me what X is without knowledge of the theorem. If we eliminated the remote interior angles concept, there is no way that you're going to be able to tell me what that angle is, okay, based off the information that's provided. Maybe if you introduce some new variables and maybe use the system equations, you could do that, okay? So maybe if I called that Y, you could tell me, I go 5x plus y equals 180. Would you agree with that? And then maybe you could say, well, y plus x plus 120, those are the angles on the inside of the triangle. Those are equal 180, right? And I think we've maybe seen enough of these to realize what work is involved in doing that, okay, if we didn't have this next theorem, okay? So we would have to go through, maybe use elimination or substitution, and that's an involved process, right? Well, understanding new theorems and understanding these new properties allows us to say, we can identify, this thing stopped working, we can identify this angle here, come on, we can identify that, apologize, I don't know why this does this. There we go. We can identify that angle there as an exterior angle, and that angle there, and that angle there as the remote interior, right? And that allows us, if we understand that logic, that allows us to go around all of that work right there and simply say that should equal x plus 120. Gives me 4x equals 120, x equals 30. Okay? Would you agree that that algebra there is much simpler than using the system of equations up there in blue? All right. If you don't have knowledge of the remote interior angles equaling the exterior angle, the sum of them equaling the exterior angle, you can still solve this problem, but you have to introduce the y, and you have to create two equations, and then use a system, and then use substitution or elimination, and you're probably still doing that math, and right now we've got the answer using the theorem. So the theorems allow us to go around more difficult, simplify our arithmetic, simplify our algebra. Is that okay with everybody? Now, I know that, so I know that's 30. That's this. And I think this is something that you guys can kind of mess around with all the time on these questions. There are other properties existing here that we haven't targeted to get this 30. We now know that's 150 degrees, right? Do you know this is, so x we said was 30, right? So that's 30. Okay? If that's 30 and that's 120, how many degrees have I used so far? 150. So that's using the property that we came up with this equation with, right? So that's not something new. But if that's 30, that's 120. What's this angle here got to be? 30. Did we ever, through the work here, compare those two angles? We never, to create the equation, we never compared those two angles. But we know they should be a linear pair, and based on the numbers that I just generated, did they become a linear pair? You see how using previously known facts, you can kind of work your way around your figures? And if you can validate other facts that you know should be true, that pretty much guarantees that I know that 30 was the right answer. Okay? Let's try this one. Lots of different ways of doing this problem. Okay? Lots of different ways of doing all of these problems. And that's the thing about geometry, and what you're going to find out as you move through other classes, that there's not just one way. Okay? And I know, because I was this student. I was a student in 9th grade, 10th grade, so just show me how to do it. Just show me one way. I'll learn that way. I'll learn it inside and out, and I will do that every single time. But this question is then followed up by this one, and what I use on this one is completely different than the ones I use on that one. Does that make sense? So I could do this one. I could use that kind of like photographic memory, and every time I saw something like that, I could redo it. But then when they changed it, I couldn't change. Okay, I couldn't adapt to that one. But if I understand the properties, I can. Okay, what's the number one thing that kind of jumps off the page here in this picture? Parallel lines. Okay, we always need to be on the lookout for those types of things. So this is bringing in that concept. So if I got parallel lines, I've got transversals, right? Okay, so let's kind of do that game that we did last time, where if we've got multiple transversals, let's get rid of one of them. And I'm just going to choose that one. You could have chosen the other one and probably found information that was useful. I'm going to choose that one. And the reason I want to choose this one is because I want you guys to see that, do you know anything about those two angles? Right? So I'm going to put 50 there. I'm going to transfer 50 there because I know it's a fact. Was that ever represented by y or x or anything in my problem? No. It's not an answer for my problem, but I know it's true. So I'm going to use it. Okay? And that's going to be something that you have to be able to kind of justify to yourself, even though they're not asking me for that angle. I know it's 50, so I can maybe put that in there, and now maybe I can use that, because now what have I got up top here? How many angles have I figured out in that triangle? I know two of them, and if you know two angles in a triangle, you automatically know the third one, right?